Okay, apologies for that. I'm going to look at getting the license so it doesn't bomb out on us at every half hour. Um, but what we've got here is we've got a range of oscillators in our object. And of course, we have uh, lots of energy. The hotter it is, more energy per wavelength is being emitted. And of course, we've got a range of oscillators. It's interesting that when you really at 5,000 Kelvin, it's interesting that even the low frequency is still coming off. So it's still being emitted. So even at the height, at the very high temperatures, there is the low frequency coming off, meaning that there must be some atoms within the solid that are not moving at the high frequency, even though the temperature is so high. There's some interesting laws around this that don't really relate to quantum mechanics, but they're interesting in describing the phenomena. And uh, Wien's displacement law just relates this maximum, this peak here per temperature. If I go back a slide or two, let me go back. No, it's in forward slide. Uh, Apologies. It's displacement law. Sorry. Um, Wien's displacement law. It relates the energy distribution max to the temperature. So as your temperature goes up, you'll see that the maximum moves bluer and the maximum's even more blue. But you can get an exact lambda max for maximum absorption based on the temperature and based on this constant. So Wien's law is really useful, but really it doesn't relate to quantum mechanics. Okay, so that's a phenomenon. I've detailed the phenomenon. Now, what I need to do is have a look at how looking at this phenomenon classically leads to problems. And the problem is with the Rayleigh-Jeans law. And Rayleigh-Jeans had a look at it and said, well, you've got an object, and it's got a lot of motion in the solid, and you've got lots of different motions within the solid, and they're all active, and all of them will give off electromagnetic radiation. And of course, um, that radiation will be dependent on wavelength. And his law came to this that the intensity coming off is proportional to 1 over lambda to the power of 4. Now, the problem with that is that as your wavelength gets smaller and smaller, as you get bluer and bluer, this never comes back down to 0. You can see that this number will go off to infinity at low wavelengths. So for ultraviolet light, the intensity coming off is really high. And it doesn't matter what the temperature is. Put the temperature to be really cold. Maybe have it at 100 Kelvin, at minus 173 Celsius. At that temperature, even if it's that small, if you have a look at the density coming off in the ultraviolet region, there's a lot of light. This predicts a lot of light coming off in that region. And so this does not match experiment nearly as well. The question is, how did he come up with this law over 1 over lambda to the fourth? Well, it's quite straightforward. The way he dealt with it is um, he looked at cavity radiation, and he said that, well, if you're going to have radiation emitted from a cavity, the first thing you've got to be able to do is you've got to set up a standing wave for that electromagnetic radiation, which means that you've got to have a perfect number of wavelengths from one side of a cavity to another, so that when it gets reflected perfectly, and that creates a perfect standing wave. You can see here, I've got it perfectly 1.5 wavelengths, absolutely perfect to there, so that when it's reflected, exactly 1.5 wavelengths come back, and that the wave, it has value 0 at the edges. So fitting that wave in is really important. The wavelength that you can fit in is really dependent on the size of that cavity. You can imagine if you made this wavelength slightly longer, it's not going to fit in this cavity, and so you can't set up a standing wave. But of course, as you make it to exactly this wavelength, which is half lambda for a very long one, it'll get reflected perfectly underneath, and you'll get a standing wave. And so for that long lambda, for that low frequency, for that long lambda, we can fit in maybe one frequency into it. However, as you increase the frequency, as you decrease the wavelength, you find that there are more modes available. You can fit it so you can get a wave that fits perfectly in various regions of the cavity. The smaller you make the wavelength, the more multiples of that wavelength you can fit in different ways into that cavity. What he was saying is that as you move towards ultraviolet, there are more ways you can set up a standing wave in a cavity. And so the more ways that you can set it up, the more that radiation would get emitted by that cavity. And so that's where the 1 over lambda comes to the fourth. You've got more ways of emitting ultraviolet light than you have of infrared. And so the object should be emitting an unbelievable amount of ultraviolet light simply at room temperatures. And that's not the case. Experiment tells us very clearly that's not the case. And so this has been termed the ultraviolet catastrophe. Okay, so the problem was with cavity radiation is that his thought was that all modes of radiation have an equal chance of being emitted. And that problem leads us to this ultraviolet catastrophe, because there are more ways to set up a short wavelength radiation, and so ultraviolet radiation will be set off. For small lambda, the energy given off will go to infinity. So there is a problem looking at this cavity radiation in a classical sense. So how did Planck sort it out? Well, Planck came back to this problem and said, well, hang on, firstly, there are two things that we need to do. Firstly, your oscillators are not allowed to have any energy value. They said that he said the energy value of each of the particles in the solid has a multiple of h nu, where h is his constant, which is very small, but n has to be a multiple and a whole number, 1, 2, 3, or 4. And secondly, he added in that there's a distribution, that not all oscillators are probable. There's a distribution of oscillators. And so, yes, you may have low frequency oscillators and high frequency oscillators, but you won't have so many high ones, and there will be a distribution among the oscillators. And so those that are higher in the distribution will give off more energy. Those that are lower in the distribution will give off less energy. And so his law came to being, the density coming off is 1 over lambda to the 5 e to the hc over that, and that matches experiment really well. I'm not going to go into more detail into Planck's formula than that, but please, if you choose that, if you choose black body radiation, you'll be able to go into a bit more detail, and you'll be able to get in your write-up, you'll have more information on that. Okay, in the next lecture tomorrow, we'll have a little bit of a look at heat capacities. So I'll introduce that, but that is one of the choices for your hand-in. And then I'll go on to some of the other things that we need, that give us a case for quantum mechanics. Okay, are there any questions about the lecture?
Prof?
Yes?
So, okay, first of all, I wanted to know, with the Zoom meeting, I think maybe the reason it cuts us off is because you set the meeting to 40 minutes and then it ends it after 40 minutes.
Yes.
So I think you can lengthen it, because you can definitely make it like 2 hours if you want.
I will need, I just need to get hold of someone in terms of a license for that. We have a license available, but I haven't got that license. So I will need to get
okay.
That.
Okay, and then please can you just explain how Planck did it differently, like his things that he said, okay, we have to do this differently?
With Rayleigh-Jeans, Rayleigh-Jeans says that everything is possible. It doesn't matter, the low frequency, high frequency are all possible. But of course, so in your solid, you've got an equal distribution. So you've got 10 at the low frequency, you've got 10 at the high frequency. Of course, the low frequency can't get rid of the energy so easily because it has to set up this wave, and there's limited ways that the low frequency can do it. But the high frequency has many ways it can set up, so there are many ways it can do it. Now, first of all, Planck says no. You don't have equal. If you've got 10 low frequency, you don't have 10 high frequency. You've got a distribution of frequencies from low to high. And this is his distribution of frequencies. That's the first thing he said. And the second thing he said is that not all energies are possible. If you limit the energies that are possible, you limit the energy coming off, and therefore you more closely match the distribution you have available. Does that?
Yeah, I think that's fine. Thank you.
But I don't want to go too much in detail because this also is part of an assignment that I'd like you to, if you choose it, to go into depth with it. Any other questions? Okay, well, if there are no further questions, please note that I do have email and you can always contact me at any stage. Please have a look at, if you haven't done the quizzes, the first quizzes. So there was a quiz number 1, which is based on the lecture that we did from in the earlier part of a week on what you can do with molecular modeling, for example. Please make sure you do those. Please, if you've got queries about any of the assignments I set, about the prac that I want you to do, please let me know. And then I'll see you again at 11 o'clock tomorrow. Okay, thank you.